concentration for a little bit. And we think that's exactly, the reason is that we have smaller particles agglomerating into bigger particles, and the dust track, of course, thinks, okay, concentration keeps going up. Our instrument, even though there's some artifacts here, and the reason for that is that at really high concentrations, the way we're measuring these things, we're essentially prone to adding some noise to it. But if you average it, you actually see that our device actually sees a decrease, okay? So that's, maybe that we're actually seeing more of the ground truth, and dust track has some artifacts. Okay, and then, of course, we're using, we're continuing analyzing the device, right? So we're using some computational fluid dynamics to optimize the design of our virtual impactor, because of course we want to make sure that we do have the right cut point, right? We want to find out what our wall losses are, et cetera, et cetera. So, this, you can see here some of our modeling actually. We're using Console to do this, and the idea is, to use this modeling. This is essentially, that's how we do microsystem designs. We model, we then fabricate, we validate the model, and then we refabricate, and eventually we end up with something that actually works pretty well. So we have this continuous cycle here as well, right? So you can see some of our modeling going on here. The problem, though, is that when it comes to the validation, our devices work at flow rates which are orders of magnitude smaller than the flow rates that are being required by some of these devices, right? And so, for example, we fabricated a die here. This is just the virtual impactor without the thermal precipitator of the F-bar. And so the idea is, let's use this to detect the cut point, right? To see exactly what the cut point is, what are the wall losses. And so the problem is that if we want to balance the flows to the